So every configure test point appears here. Every result is displayed here, and every final evaluation is generated from this section. So let's explain this table in detail. So the test table, as we explained, is the main execution and the monitoring area inside the meter module, and every line here is visualized and displayed in the table represents one complete test point. So this table contains all the configured parameters, the measured results, the timing information, the tolerance limits, and the final pass or fail evaluation. So in practical testing, this becomes the main working area for us because all configured tests are stored and executed from here. So simply you can add a new test line, as we explained. Whenever the required settings are prepared inside the test tab, the add button is used also to create a new test line. And the new test line will be automatically appended at the end of the test table, and this allows you to gradually build a complete test sequence step by step. So let's explain this column meanings. So the first one is the evaluation column. So it displays the final evaluation status of the test line. It can be not tested, as you can see from here now. So if the test has not been executed or started yet, the line shows not tested status. If it's passed, it will be with greenish check mark. If it's failed, it will be with a red cross, which indicates that the error is the measured error exceeds the allowed tolerance and the line is failed. Also, it can be out of range. If the generated quantity exceeds the hardware capability of the test set, the line is marked as out of range and the test is not executed. Also, it can indicate overload conditions occur during the testing. So the meter module still evaluates the point and indicates whether the result passed or failed under overload conditions. Then the second column, which is the mode here. So the mode column displays the test mode used for a specific test line. For example, L here representing the load test. If it's M representing the mechanism test, N representing the no-load test, C representing the creep test, and so on. Then we have the voltage column, as you can see. So the V column here displays the phase to neutral voltage for balanced system. So if this system is unbalanced, this column displays unbalanced instead. And if the voltages are different between phases, as you can see from here, so it will be indicates as varied. Okay, so the table displays the word varied. So if you change these values to be unbalanced, as you can see from here, then you can click update. So now the V column is displayed as varied, which means different voltage values. And if you move the cursor, as we see now, it will display the tooltip to give you indication about the three voltage values of the three phases. Then we have the current column, as you can see from here. So the current column displays the test current values. So just like the voltage column, balanced system shows the column current value, while the unbalanced system shows the unbalanced indication. Also, if the phase current are different, if you move the mouse, it will give you a tooltip also to display all the phase current in this tooltip. Then we have the cosine phi table, as you can see from here, to display the power factor used during this test. Also, for the balanced system, the actual power factor is shown directly, but for the unbalanced system, the test displays the unbalanced indication instead. Then we have the nominal quantity. So the nominal quantity column displays the target quantity expected during the test, and the displayed unit depends on the selected meter type and the selected measured quantity. Then we have here the pulses, the pulses column. So the pulses column displays the required number of pulses needed to complete this test. So I define this test line to have only one pulse, and here is a timestamp column as well. So the time column also displays the expected test duration based on the selected quantities and the meter constant. So in the pulses column here, in the most tests, the pulse count is actually the stopping condition used by the meter module. So once the required pulse count is reached, the test automatically finishes. So as we explained, there is one important information here, that the pulses, the energy and time all mathematically linked together, as we explained, through the meter constant. So changing one value will automatically affect the other two values. And also we have here the runs column, as you can see. So the runs column also defines how many times the same test line should be executed. And if this value of the test runs is 0, which means the test universe will skip this line. So the test line will be skipped completely during the automatic execution. For example, if I set the test run as 0 and add 1, so this test value will be, or test line will be skipped during the automatic execution of the test tables. And if you select a multiple runs, as we explained before, the meter module will repeat the tests several times based on your setting, and it will calculate the average values and the standard deviation. Then we have the tolerance column, which displays the acceptable error limit used for evaluating the result. Normally, this value comes directly from the selected meter class, as we explained, and however, the operator may also need to manually adjust this tolerance for specific test conditions or test currents. Then we have the result column, so it will display the final measurement result. And this result also can be displayed as accuracy if this option is enabled, which is results as accuracies. So the result column will be displayed as accuracy value in percentage, or if it's disabled, the result as accuracy, so the result here will display the error. Okay, so it will be the error value instead of the accuracy value. So when several runs are performed, also the meter module displays average value together, whatever its accuracy or error. Then we have here the number column, so it displays the line number, like number 1, this is the line number 1, this is line number 2, and so on. So as you can see here, the tabs. So if you are working with normal energy meters like watt hour meter or var hour meter or volt ampere hour meter, so this table contains only one tab corresponding to the selected meter type and the selected measured quantity. But if you select from test object the meter type to be a multifunctional type, so now you can have a different tabs from here. So by navigating to the setting tab, you can display different quantities, as you can see. And then once you get back, you will find a different tabs, and this allows you to continue all the tests with independently between different energy quantities. Now let us continue with the graphical visualization tool available inside the meter module, which is the phasor view, as you can see from here. So the vector diagram is located in the upper section of the phasor view, as you can see, and it provides you a graphical representation of the voltage and the current vectors. So the diagram here can display both balanced or unbalanced phasors. Also, the vector diagram is extremely useful because it gives you visual confirmation of the applied phase relationships, and it helps you quickly identify any incorrect phase angles or wrong phase rotation or wiring problems. So simply, if you right click, you can display the helper lines, as you can see from here, which shows or hides the diagonal helper lines, which used for can be used for easier angle visualization. Also, we have here the rotate V option, which defines whether the voltage system remains fixed when adjusting system angles. Also, we have here select colors, so you can change the color for the background or the foreground or the helper lines or voltage or current, or you can return it back to the default colors. For example, you can now change the foreground colors to be black, for example. So it will be black, as you can see. Also, you can change the foreground or the background or the helper lines, as you can see from here, to be in red. So now it gives you better visualization. Also, you can change the background, as you can see from here, to be in yellow, for example. So it will give you better customization of the phasor view. Then we have here the power view. So the power vector diagram also displays the active, reactive, and the apparent power vectors, and also it can be indicated as a PQ plane, as you can see, for the fourth quadrant. It gives you also information about the type of load, is it capacitive or inductive. So this displayed values represent the complete three-phase power system. So it doesn't only display the individual phase powers separately, it's a combined three-phase power system. So even under symmetrical load conditions, the diagram still displays the resulting total 3 phase power vectors, and this diagram is very useful for understanding the overall power conditions applied during testing, and it gives you also a quick visual understanding of the power flow direction and the power factor conditions. So to give you an example, for if you change this angle value or the power angle to be 30 degree, for example, so now you can see the power, you can see the reactive power and the apparent power relationship based on the phasor relationship between the voltage and the current. So here the active power indicates by P, the reactive power indicates by Q, and the apparent power indicates by S. So this diagram helps you to quickly understand the overall power conditions being applied during the testing. Also, you can see whether the system is inductive or capacitive. Also, the direction of the reactive power flow and the relationship between the active and the apparent power. And this becomes especially useful during the advanced testing involving the phase angle changes or reactive power conditions. Just like the normal vector diagram, also the power vector updates continuously whenever the operator changes the generated quantities. Also, you can customize the colors as we explained, or you can display the helper lines as we did in the phasor view in the upper part. Also, you can customize the background, the foreground, the helper lines, or the vector lines. For example, we can customize now the background to be in blue, for example. So you can see now it's in blue, or you can change it to a different color for a better visibility, like in green. So now you can customize both of the phasor view or the power vector views. So the background colors, as we explained, it can be used for changing the background color option. Also, we have also the foreground color option here, which can be used to change the labels, borders, and the diagram elements. Also, we have here the helper lines, which gives you better visibility about the diagonal reference lines. Also, we have here the vector colors, as you can see, which allows you for displaying the power vector themselves, and the default color for sure, which restores the original default appearance of the power vector diagram, as you can see from here. So together, the vector diagram and the power vector diagram provide a complete graphical understanding of the electrical condition generated during the testing, and instead of relying on the numerical values, the operator also can immediately verify the complete system behavior visually, and this significantly improve troubleshooting speed and reduce the possibility of wiring mistakes or incorrect phase angle settings.